Earth. For us, this is home, the only home we have ever known. Our planet is a wonderfully complex world covered with vast oceans and warmed by an above-average yellow star. Surrounded by a thin, life-sustaining atmosphere, Earth is adrift in a sea of cosmic dust and gas. Hurtling through space at 30 kilometers per second, it takes 1 year or 365 days to complete one orbit around the Sun. Our Sun shepherds its entourage of planets, comets, and asteroids on a 200 million year-long journey around the center of our home galaxy, the Milky Way. With a visible diameter of 100,000 light-years, our galaxy is just a small component in the large, web-like structure of the universe. Clusters upon clusters of galaxies meander across vast expanses of empty space. The Milky Way galaxy has spiral arms comprised of an estimated 300 billion stars. Despite its great size, it is only a speck in relation to the entire cosmic arena. The universe is about 13.7 billion years old, yet only during the last 100 years have we discovered most of what we know about its age, vastness, origin, evolution, and our place within it.
This modern picture of the universe stands in stark contrast to a previous model that placed the Earth at the center, regarded the Sun and Moon as planets, and attached all planets and stars to crystalline spheres that rotated about a stationary Earth. The foundations for building this cosmic model were laid in ancient Greece, one of the major centers for the development of rational thought. We find our scientific heritage in the observations, writings, and innovations of Pythagoras, Archimedes, Plato, Aristotle, Aristarchus, and others. As they grappled with the fundamental questions about our origins and the origin of the universe, the philosophers laid the foundations for the gaining of knowledge through scientific inquiry. The Earth-centered model of the Greeks was based on the motions of the fixed stars and the 7 celestial bodies across the sky: the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. During the daylight hours, the Sun rises in the east and sets in the west. The Moon, too, travels east to west across the sky, though at a slightly different rate than the Sun. As a result, their relative positions in the sky constantly change, leading to the monthly cycle of the phases of the Moon. At night, the stars and constellations take a similar path from east to west. Through close observation, the Greeks noticed that the stars travel with a different speed from the Sun and the Moon. The Greeks also observed a handful of capricious stars that appeared to wander randomly amidst the background of the constellations. These wandering celestial bodies are what we now call planets. Any model of the universe formulated by the Greek natural philosophers sought to explain the peculiar motions of these objects. Our senses tell us that the Earth is not moving under our feet. The circling of the stars reasonably positions us in the center of it all. This illusion prompted the Greeks to construct a model of the universe that placed a motionless Earth at its center. The Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and the stars were fixed to 8 transparent ethereal spheres. The rotation of these spheres about the Earth produced the observed motion of the planets. In ancient Greece, the divinity of the sphere would have made it the only geometric shape capable of describing the constancy and perfection of the heavens. With each celestial body possessing its own rate of motion, each body would have to be placed on its own celestial sphere, requiring a nested set of concentric spheres to describe the heavens. Aristotle believed that change occurs as objects, animals, and people seek their divine purpose. The divinity of the planetary orbs required them to be unchanging. They could not speed up, slow down, or wax and wane in brightness. Therefore, the motion that we detect for them is eternal. In its infancy, the Greek Earth-centered model was questioned by one of the greatest astronomers of the time, Aristarchus of Samos. Aristarchus had developed an alternative model of the universe, one in which the Earth rotates once per day on its own axis, and, most importantly, travels through space in orbit about the Sun. Aristarchus's sun-centered model efficiently explains why Mercury and Venus never stray far from the Sun, and why planets like Mars, Jupiter, and Saturn stop abruptly in their seasonal west to east progression, reverse course, and then continue on their journey. Why Aristarchus's model did not take root in the ancient world is not entirely clear. Perhaps the Greeks needed a physical reason for the Earth and the other celestial bodies to travel around the Sun. At the same time, Aristotle's physics gave a good rationale as to why the Earth is the center, since everything made of matter falls toward the center of the Earth as it seeks its purpose. If the Earth were no longer the center of the universe, why do material objects fall down when dropped? Of course, Aristarchus was unable to provide even a rudimentary understanding of a mutually attractive force that might cause both objects to fall toward Earth and objects to orbit one another. Aristotle also had ruled out the possibility of the sun-centered universe on the basis of another observation of the night sky. He noted the lack of something astronomers today refer to as parallax. Aristotle reasoned that if the Earth really did orbit the Sun, nearby stars would change their positions in the sky with respect to more distant stars as the Earth changed position in its orbit about the Sun. However, when Greek astronomers searched for evidence of parallax, they found none. The lack of measurable parallax could mean that the Earth does not orbit the Sun. Of course, this is what the Greeks concluded. However, the Greeks also could have concluded that the distance to the stars is so great that the effect of parallax is too small for them to measure. While the Greeks did not know the distances to the stars, they assumed that they could not be that far from the Earth. And so Aristarchus's model did not gain acceptance and faded into obscurity. As time passed and observations improved, it became clear that the geocentric model failed to accurately predict the future positions and motions of the planets. While some philosophers and mathematicians altered the model, they never questioned its fundamental precepts. As a result, the original straightforward model of divinely perfected orbs rotating with constant speed on perfect circular paths got more complicated. Apollonius of Perga was the first to assault the model's simplicity. He added additional circular motions called epicycles to the already spinning planets. These circles on top of circles accounted for the anomalous retrograde motion of the planets, as well as explained the seasonal variations in their orbital speeds. Ptolemy would later perfect the addition of epicycles by offsetting the Earth from the geometric center of the model. By doing so, Ptolemy broke with traditional Aristotelian physics in an attempt to save the appearances of Greek cosmology. Despite this fundamental change to the structure of the universe and violation of Aristotelian philosophy, thinkers of this time and for the next 1,000 years maintained the validity of both Aristotelian physics and the pseudo-geocentric model of the universe. The result was to transform these earliest attempts at scientific investigation of the natural world into a dogmatic prescription of the universe. Despite Ptolemy's improvements, discrepancies between the model's predictions and the observed positions of the planetary bodies became obvious. Still, little was done to reform the model. History would have to wait until a canon of the Catholic Church, living in a remote outpost of what is today Poland, decided to challenge the doctrine and dogma of the Greek universe. Nicholas Copernicus attempted to reform Aristotelian cosmology and physics by placing the sun at the center of the universe. In effect, he set the Earth in motion, as Aristarchus attempted long ago. However, Copernicus failed to cast off all remnants of the previous model, dutifully retaining the Pythagorean and Aristotelian tradition of placing the planets on circular orbits. Today, we know that the planets move on elliptical, not circular orbits. As a result, Copernicus's sun-centered model also required epicycles to accurately predict planetary positions. Despite these complications, Copernicus's model was quickly adopted by those interested in predicting planetary motions. The necessity of introducing epicycles to the heliocentric model went against Copernicus's goal of simplifying our model of the universe. Combined with the revolutionary notion of moving the Earth from the center of the universe, the church canon would not publish his calculations of planetary motions until a young Lutheran mathematician and disciple, Georg Joachim Rheticus, convinced him of the value of his work. In dramatic fashion, the final printed manuscript was delivered to Copernicus on May 24, 1543, the day he died. Sadly, Copernicus never lived to see the fruits of his labor in the revolution he helped to begin. Support for the heliocentric model was slow to build. The revolutionary mantle would be picked up in the late 1500s by a young German mathematician, Johannes Kepler. While Kepler had his own metaphysical notions about the workings of the universe, his primary goal was to fit his models to the motion of the heavens. Kepler did not have the means to improve upon the observations of the Greek and Arab astronomers. However, a contemporary of his, the Danish astronomer Tycho Brahe, was busy mapping the sky to greater accuracy than had ever been achieved. Tycho became interested in astronomy after observing a supernova in 1572. Afterward, he would dedicate the rest of his life to measuring the sky. His observations of stellar positions were enabled by the generosity of the King of Denmark, who gave Tycho the island of Aveni and the means to construct a castle observatory called Uraniborg. Tycho would become the lord of Uraniborg, the island, and the servants who assisted him with his astronomical pursuits. Using oversized tools, he measured stellar positions with an accuracy that would not be surpassed until the invention of the telescope. Tycho the observer and Kepler the mathematician found one another during a tumultuous time in European history, when Tycho hired Kepler to work for him. However, Tycho died unexpectedly, leaving behind a trove of positional data the obsessive Kepler could use to prove the heliocentric model of the universe. Kepler used Tycho's data to determine that the orbits of the planets are elliptical, not circular. Elliptical orbits simplified Copernicus's sun-centered model by removing the need for epicycles, a simplification Copernicus had likely envisioned, but was unable to reach due to his adherence to the divinity of circular motion. At the same time that Kepler published the results of his work, an Italian mathematician and natural scientist named Galileo Galilei pointed the newly invented telescope skyward. He found mountains on the moon, innumerable stars in the Milky Way, blemishes on the sun, new planets orbiting Jupiter, and not the Earth, and the phases of Venus. These observations contradicted Aristotle's conception of the heavens and provided support for a sun-centered universe. Galileo would go on to famously challenge the Catholic Church over the Earth's position in the universe and its interpretation of Scripture. He was found guilty of heresy, forced to renounce the Copernican model of the universe, and sentenced to house arrest for the remainder of his life. And so Copernicus, Tycho, Kepler, and Galileo, with their revolutionary spirits, unfailing attention to detail, and undeniable pursuit of truth, collectively moved the Earth from the center of the universe to its rightful place in the heavens. In the new view of the universe, the Earth became a planet, orbiting one of a multitude of stars. The question of our origins took on a different meaning. The one-time fringe opinion that an infinity of worlds exists in the universe gained instant legitimacy. No longer the focal point, Earth became immersed in the obscurity of a vast universe. By the mid to late 18th century, mathematicians and philosophers alike were developing scientific theories of star formation. Mathematician Pierre-Simon de Laplace and philosopher Immanuel Kant are both credited with contributing to a star formation theory known as the nebular hypothesis. Rooted in observation and based on a fundamental physical understanding of nature, the nebular hypothesis predicts that the solar system began as a cold, dark cloud of gas and dust. Gravity, the mutual attractive force between massive objects, would force the cloud to collapse onto itself. Laplace and Kant reasoned that a large cloud could shrink enough due to its own gravity to form a spherical star. Gravitational energy from the collapsing cloud would be converted to thermal energy, making the young star shine. While gravity alone explains the formation of the star, additional knowledge of how nature works is required to understand the nebular hypothesis explanation of the formation of a planetary system. In any physics classroom, it is often stated that energy can be neither created nor destroyed. As an example, let's think of dropping a ball from some height. Before the ball is dropped, it is not moving. However, it has energy due to its position with respect to the ground. This potential energy is due to the gravitational force acting between the ball and the Earth. After the ball is released and accelerates toward the ground, its potential energy converts into kinetic energy, or the energy of motion. As the ball gets closer to the ground, more and more potential energy is converted to kinetic energy, and the speed of the ball increases until it hits the ground. Throughout the descent, the total energy of the ball remains unchanged. At the moment the ball contacts the ground, the energy due to its motion is equal to the energy it possessed before it was dropped. If the ball could bounce off the floor without losing some of its energy to the ground, it would bounce back to exactly its initial height. Thus, the energy this ball possesses due to its motion and position remains constant. Energy is said to be conserved. In a collapsing cloud, the conservation of energy leads to the heating of the forming star. A second, similarly conserved quantity is the key to understanding the formation of planetary systems. Let's return to our collapsing cloud and make the assumption that it rotates. The cloud's rotation ties directly to another fundamental conserved quantity, angular momentum. The angular momentum of an object depends on three things: its mass, speed, and the distance from the axis about which it is rotating. Imagine a spherical cloud. Let's focus in on one little parcel of gas within this cloud. As the parcel spirals inward, its distance from the rotational axis decreases. The mass of the parcel remains the same. In order to maintain its initial angular momentum, the speed of the parcel must increase by just enough to balance the decrease in distance from the center. Therefore, the conservation of angular momentum causes the cloud to spin faster as it shrinks. Competitive figure skaters use this conservation law to dazzling effect, spinning so fast that they often appear as a blur. How does the increase in the rotation rate of the cloud tie into the formation of planets?
If we were to place ourselves in the skates of the figure skater, we would notice that it becomes harder and harder to bring your arms in as they get closer to your body.
As you rotate faster and faster, the force needed to keep our arms moving in circular motion increases. While the ice skater is strong enough to pull their hands all the way inward, the gravitational force directed toward the center of the collapsing cloud does not increase enough to pull the entire cloud to a central point. Our parcel of gas will reach a distance from the rotational axis where the gravitational force is no longer greater than the force required to keep the parcel in circular motion. When these forces balance, the inward spiral stops. However, gravity is still pulling the parcel toward the equatorial plane of the cloud, parallel to the rotational axis. This component of the parcel's motion is unaffected by the conservation of angular momentum. The result is a pile-up of gas and dust along the equator of the rotating cloud, resulting in the formation of a flattened disk of material. Using basic physical principles, the nebular hypothesis describes how a planetary system in which all the planets lie nearly in the same plane and orbit their star in the same direction could have begun as a cloud of gas and dust. In the mid-18th century, when the nebular hypothesis was first formulated, there was no evidence that stars were still forming in the universe or that other solar systems ever existed. In the following centuries, our model of the universe grew larger as billions of galaxies other than the Milky Way were discovered. Edwin Hubble would discover the expansion of the universe, leading to the conclusion that the universe must have had a beginning. Evidently, the universe has not always existed and has been evolving for billions of years. Evidence of such change can be observed in the dramatic explosion of dying massive stars, such as the one Tycho Brahe observed. So if it is possible to observe the deaths of stars, can we observe their births? According to the nebular hypothesis, the search for the origins of solar systems leads directly to cold, dark clouds of dust and gas residing in the Milky Way. By the late 1970s, astronomers were finding evidence that these clouds of dust and gas would eventually form into disk-like structures. And as predicted, over 250 years after the invention of the nebular hypothesis, young stars were found forming in these clouds. However, real confirmation of this would only come once astronomers pointed the Hubble telescope at one of the nearest regions of active formation, the Orion Nebula. These disk-like structures were dubbed protoplanetary disks, or proplids, a term indicating their future status as planetary systems. These proplids exist around most stars when they're about 1 million years old, or 1/5000th of our Sun's present age. But due to their density, we can view them only as silhouettes on the more distant glow of the nebula, casting tiny shadows in our direction from hundreds of light years away. There is little doubt that the secrets to understanding the origins of the solar system rest in the study of the processes at work in these systems. Today, observatories around the globe, along with those we have launched into space, open new windows into these young planetary systems. The capability of detecting infrared radiation from young stars allows us to directly study the cool, dusty disk material. At the other end of the spectrum, space-based X-ray telescopes provide us with a glimpse at the high-energy phenomena occurring near the surfaces of the forming star. Young star systems turn out to be quite violent environments. Material continually crashes onto the surface of the forming star, while other material is superheated by strong magnetic fields in their coronae. Both processes produce high-energy X-ray photons. Such high-energy photons may impede the formation of planetary systems by heating and boiling away the disk. Using NASA's space-based Chandra X-ray Observatory, we can study the X-ray emissions in these systems. For example, in this X-ray movie of the Orion Nebula, we see numerous sources displaying considerable variability in the strength of their emission. In order to study the impact these X-rays have on the lifetimes of planet-forming disks and the likelihood of planet formation, Colgate astronomy students working with Professor Jeff Bary and collaborators Greg Hertzeg from the Max Planck Institute for Extraterrestrial Physics, Rodolfo Montes, and Joel Kastner from the Rochester Institute of Technology are using the Chandra X-ray Observatory in conjunction with the Gemini North Observatory in Mauna Kea, Hawaii. The group is searching for correlations between X-ray variability and emission from gases in the disks that may indicate the effects of X-rays. At the cutting edge of today's research into the formation of planetary systems, this research program has as its legacy the work of all the great thinkers and scientists that have come before. Our historical journey has shown that human thought and understanding, including our ways of gaining knowledge about the natural world, has changed dramatically over the centuries.
And that by pointing our powerful telescopes outward and peering into the hearts of active regions of star formation, we discover that the making of a star and her entourage is the key to unraveling the secrets of our own origin.